Hi there, folks. Today we're looking at adding and subtracting and multiplying polynomials. And this is some of those things we've done before, but we're just going to kind of reiterate them and maybe take some of these things up a notch. And when we're looking at this, starting with addition and subtraction is just simply just us combining like terms. All right, and when we do that, if it's addition, obviously we'll add like terms. If it's subtraction, we can subtract like terms. But my recommendation when you have subtraction is to actually change it to adding the opposite. Okay, so instead of actually doing subtraction, we'll change that to adding the opposite, and then we're just going to do addition instead, which is just combining like terms. Okay, so when we look at an example here, remember that like terms are terms that have the same variables with the exact same exponents. So the variable portion has to look exactly the same. So when I look at this first example, here the 3x cubed and the 1x cubed are like terms because the variable portions are exactly the same. So I add the coefficients, the variable part stays the same, so that's going to be a 4x cubed. All right. Here the 2x squared and the negative 10x squared, those are like terms. When I add those together, it's going to give me a negative 8x squared. Here the negative x doesn't have a like term. So basically, I'm going to add nothing to it, which means it stays the same, so it's going to stay as a negative x. And then the negative 7 has a like term with the positive 8, and when I add those together, it gives me a positive 1. And that's it. So I'm combining like terms, I'm adding the coefficients, the variable portion stays the same. All right? If I look at the next one, I approach it the same way. I'm looking for like terms. Here the 9x cubed doesn't have any like terms, so I add nothing to it, so it stays as a 9x cubed. Next, I see this 5x squared over here, but there's no 5x squared in the first term, so again, it's like I add nothing to it, so it stays as a 5x squared. And the reason I looked at that term next is because I'm trying to do these in descending order. All right. Now I can look at the negative 2x and the plus 12x. Those are like terms, so they add to a 10x. And then the 1 and the negative 4 are like terms, and they add to a negative 3. Okay, so I'm just combining those like terms. When I look at the next one, in this one I could do subtraction. I could take this guy minus this guy, and then this guy minus this guy, and then this one minus this, and then this minus this. But what happens is we tend to forget about the minus sign. We tend to forget about the operation as we get further and further into this polynomial. So my recommendation here is to change this to adding the opposite. So instead of subtracting, I'm going to change this to adding. And then I'm just going to take the opposite of each of the terms in here. So it becomes a negative 2x cubed, a negative 6x squared, a plus 1x, and a minus 1. All right. Now I've changed it to adding the opposite. Now it's just a matter of combining like terms. The 8x cubed and the negative 2x cubed, those combine to give me a 6x cubed. The negative 3x squared and the negative 6x squared give me a negative 9x squared. And again, that's one where we tend to make mistakes if we don't change this to adding the opposite. The negative 2x and the plus 1x is a negative x, and the plus 9 and the minus 1 gives me a plus 8. And that's it. Okay, so change it to adding the opposite, then combine like terms. Same thing with the next one. I've got subtraction here, which I'm going to change to adding the opposite. Now I'm just adding, so I combine like terms. The 2x squared and the negative 3x squared is a negative 1x squared. The 3x and the negative 1x is a plus 2x. And then the 4 doesn't have any like terms, so it just stays as a plus 4. Notice it's a plus 4. That's the one we really tend to mess up when we don't change it to adding the opposite. We tend to write that as a minus 4, but keep in mind, it's like nothing minus a negative 4. It's adding the opposite. It's a plus 4. Okay? Moving on to multiplication. Multiplication is essentially us just using our distributive property. And when we use our distributive property here, we just distribute each term of the first polynomial into the second polynomial. Okay? So in this one, I'm going to distribute the x to each of these terms, and I multiply as I go using my rules of exponents. So x times a 3x squared is a 3x cubed. Remember, where you multiply, you add the exponents. Here, that's going to be a minus 2x squared, and then a minus 4x. And now I distribute the next term. I distribute this negative 3. And yeah, keep in mind that is a negative 3. We take that entire term and distribute it. So we're distributing a negative 3 there. Okay? So make sure you're distributing the negative 3, not just a 3. And when I do that, that's going to give me a negative 9x squared, a plus 6x, and a plus 12. And now from here, I just combine like terms. The x squareds are like terms, so that's going to give me a negative 11x squared. The negative 4x and the plus 6x is a plus 2x. And everything else just kind of tags along for the ride. And that's it. All right. If I look at the next one, I kind of have to just work left to right on this guy. And when I do that, I'm essentially going to ignore this third polynomial for a second. I'm just going to multiply the first two. So here I'm going to distribute the x, distribute the negative 1. And when I do that, I end up with an x squared plus 4x minus x minus 4. This other polynomial is just going to kind of tag along for the ride for now. Inside here I combine like terms. That's going to be a plus 3x and a minus 4. And now I have a trinomial times a binomial. I do the same thing. I'm going to distribute each term. And I can either distribute it this way, distribute the x squared, and then distribute the 3x, and then distribute the negative 4. Most of us find that uncomfortable, so if you want to distribute backwards, distribute the binomial. Most students find this more comfortable. So I distribute the x, and then distribute the 3. Okay? Because now it's essentially the same thing we just did in the previous example. And so when I do that, I end up with an x cubed plus 3x squared minus 4x plus 3x squared plus 9x and a minus 12. And now from here I have to combine like terms. And it looks like I've run out of space here, so let me clear some of this, give myself a little bit more space and move some things around. Now I can combine those like terms, all right? So when I do that, I end up with an x cubed, I end up with a 6x squared, I end up with a plus 5x, and I end up with a minus 12. And that's it, all right? So I'm using my distributive property twice in that particular example. If I look at this one, here I'm multiplying two things, and you should recognize that what I'm multiplying here is conjugates. And so with conjugates, remember, you can take a little bit of a shortcut. With conjugates, the middle terms are always going to cancel. So with this, I could just do the first terms, the 4x times the 4x, which gives me a 16x squared, and then the last terms, which gives me a negative 25, okay? If you just use your distributive property and multiply this out, you don't have to know that shortcut. You will get the same thing. Here I get a 16x squared plus 20x. When I distribute the negative 5, I get a minus 20x and a minus 25. And now we can see when we combine these like terms, the middle terms cancel each other out, give me a 0. Which leads to the same result that I got before. So just remember, when you're multiplying conjugates, you can take a little bit of a shortcut there. All right? Here I'm distributing two individual terms. So here I distribute the 3x. That leaves me with a 3x squared minus 21x. And I wrote a 12x like a crazy person. Let me try that again. Here I'm distributing the negative 4. And again, the big thing here is making sure you understand that that is a negative 4. So it's a negative 4x squared minus 4x. Plus 32, and now combining like terms, that's a 3x. Sorry, I missed one of the x squareds. That's a negative 1x squared, a minus 25x, and a plus 32. All right, so just make sure that you're distributing that negative. If I look at this one, squaring a term, if I want to do x plus 4 squared, keep in mind what that means. That means that I have 3 times x plus 4 times x plus 4. That's what x plus 4 squared means. It means I have x plus 4 times itself twice. And now I'm going to multiply this out. You can distribute the 3, or you can multiply the two binomials first. Because multiplication is commutative, you can do it in any order. So this one, I'm going to multiply out the two binomials first. That's going to give me an x squared plus 8x plus 16. And I've taken a little bit of a shortcut there and already combined the like terms. Now I distribute the 3. That gives me a 3x squared, a plus 24x, and a plus 48. Okay? If I look at this one, I'm doing the same thing, except now I have 3 of this term, so I have 3x minus 2 times 3x minus 2 times 3x minus 2. That's what raising something to the third power really means. So now I'm going to multiply the first two out. That's going to give me a 9x squared, a minus 12x, and a plus 4. All right, and again, I took a little bit of a shortcut there and combined the like terms already. But now from here, I've got a binomial and a trinomial. I can distribute this. I'm going to distribute the the trinomial into the binomial just so you can see that. When I distribute the 9x squared, it gives me a 27x cubed minus 18x squared. And then when I distribute the negative 12x, it gives me a negative 36x and a plus 24x. And then when I distribute the 36x squared, and then when I distribute the 4, it gives me a plus 12x and a minus 8. And now I can combine like terms. And the nice thing about distributing this way is we can see that my like terms are all right next to each other. So this one, that gives me a negative 54 x squared. This one gives me a plus 48x. And then the minus 8 doesn't have anything to combine with. And that's it. All right. And we can see right away how cumbersome this can be as soon as I start getting these exponents that are a little bit bigger. Squaring something's not too bad. Cubing something took quite a bit more work. So we can imagine, well, what's going to happen if I want to do something like this, x plus 5 to the 4th, or x minus 6 to the 7th. That's going to take a ton of work to multiply all that out. So we're going to have a little bit of a shortcut that we can use here. And this is called binomial expansion, all right? Because basically we're going to take a binomial and raise it to a power, and we're going to use this thing over here off to the side called Pascal's triangle, okay? Pascal's triangle essentially gives us this pattern that we can use to multiply out these binomials. Notice this is the 0 power, the 1st power, the 2nd power, the 3rd power, the 4th power, the 5th power, and this pattern can continue as we look at Pascal's triangle. Pascal's triangle, really we're just adding the term to the term next to it, all right? So when you look at this, here I've got 1 plus the term next to it is nothing, so 1 plus nothing is a 1, and that's where I get this guy. Same thing on this side, 1 plus nothing gives me the 1. Over here, 1 plus 1 gives me the 2. 1 plus nothing gives me the 1. So I'm essentially adding the terms that are next to each other, and it gives me the term that goes underneath it. See here, the 1 plus the 2 gives me the 3. The 1 plus nothing gives me the 1. And I can keep going. Here, the 1 and the 3 add up to a 4. Here, the 3 and the 3 add up to a 6. All right? And so I can continue this pattern. And so if we needed the next row for something, I would just say this. Okay, 1 plus nothing gives me the 1. 1 plus 5 gives me a 6. 5 plus 10 gives me a 15. 10 plus 10 is a 20. 10 plus 5 is a 15. 5 plus 1 is a 6. 1 plus nothing is a 1. Okay, and I can continue that pattern. So we're going to use Pascal's triangle, and here's how we use this thing. As you look off to the side here, we're looking for this pattern. Well, this is just 1, so when I raise a binomial to the 1st power, I get the first line of Pascal's triangle, which is a 1. When I raise it to the 1st power, well, now I use those coefficients from Pascal's triangle, the 1 and the 1, and I write a in descending order. This is a to the 1st and then a to the 0. And then this is b to the 1st and then b to the 0 going backwards. And it's hard to see at first, but as we continue, it should become a little bit clearer. If I look at the next one, it's got the coefficients as Pascal's triangle, the 1, the 2, and the 1. And notice a in descending order. See, a to the 2nd, a to the 1st, a to the 0. And then b goes reverse of that. B to the 2nd, b to the 1st, b to the 0. And then when I look at the next line, again, I'm using Pascal's triangle as the coefficients, the 1, the 3, and the 1. This was to the 3rd power, and look at the a values. A to the 3rd, a to the 2nd, a to the 1st, a to the 0. And now look at the b values, b to the 3rd, b to the 2nd, b to the 1st, b to the 0. And so I fill out this pattern in terms of a's and b's, and I can see the same thing with the next one. Sorry, I erased a little bit too much there. I can see the same thing with the next one. I have my coefficients, and then a's in descending order, a to the 4th, 3rd, 2nd, 1st, 0. And then b to the 4th is at the back, working my way the other way, b to the 3rd, b to the 2nd, b to the 1st, b to the 0. Okay? And so what I'm going to do is I'm going to fill this in terms of a and b, just like I see here on this pattern. And then I'm going to plug in the a and the b values that I have. So let's take a look at one of those examples.